end of last week, the topic had gotten to probability. That was where we left it last week. And I had said that probability is the foundation on which statistics is built. And today, you will see why that is the case. We saw that we can do things like turn a frequency table that has, classes and frequencies. We saw that we could turn it into a probability table. So maybe we'll use the classic how long I'm waiting, or let's do the commute time one. That seems easy. So my commute time 0 to 9 minutes, and then 10 to 19, and 20 to 29. And this is a small town, so nobody has more than a 29-minute commute. I guess not that small. It's kind of big. I'm surveying some people, and 15 were here, and 25 were here, and 10 were here. So then that's a grand total of 50 people that I surveyed. I could attach to this a relative frequency column, and then this would be 15 out of 50, and this would be 25 out of 50, and this would be 10 out of 50, and this equates to 30%, which is 0.3, and this is 0.5, this is 0.2, and if you add all that up, you get 1. And what we did was we said we could relabel this as event and probability. And then, boom, it's a probability table. And then now I could ask you questions like, what's the probability that one of these, that from these 50 people, I picked one at random, what's the probability their commute time was between 10 and 19 minutes? And the answer would be, well, the probability is half, because that's the row associated with this event. Okay. Now, think back to so here in red is our probability table, but it's the same as the relative frequency table. And with this frequency table, wasn't there something that it was associated with always?
Histogram.
A histogram. In fact, there's a one-to-one correspondence always with the histogram. But if this relative frequency table is constructed from the frequency table, then you also have a correspondence between a relative frequency table or a probability distribution and a histogram. So let's draw what the histogram would look like for this probability table. There's 10 and 20 and 30. And the first bar has a height of 0.3, and the second bar has a height of 0.5, and the third bar has a height of 0.2. Right. And you can see that, so it's like there's 0.1, 0.2, 0.3, 0.4, 0.5. And the heights of my bars correspond to the values on the y-axis. The heights of my bars correspond to the values on the y-axis. And my x-axis down here is like a piece of a number line. It's the number line. Like literally, this is graphed in the plane, like the xy plane. And what's the shape of this distribution? It's approximately normal. And what was our strategy for determining that? That's the two criteria that a normal distribution must have, right? But if I just give you a random old frequency distribution, how do you determine the shape of its distribution? I used the wrong word. I give you a random histogram. It does all kinds of weird stuff. Definitely not normal. How do I generate the shape of the distribution?
Split down the middle?
That would be if I wanted to determine symmetry, right? So my histogram might look like this. It's symmetric. I split it down the middle. But I want to determine, I can see that this is some kind of U-shape distribution. And what did we do?
Draw a curved line along the top.
Yeah, tops of the middle of each bar. And give it a smooth curve. And you're making this smooth curve because the presumption is that if you increase the number of people that you survey and make the classes smaller and smaller, that eventually it would just make a nice smooth curve. As the classes get smaller and smaller, the bars get narrower and narrower, but you would still have pretty much that same shape. Okay, so then we can see down here that by that strategy, this would be approximately normal. So that conceivably, if I was asking 500,000 people about their commute times, and my events were 0 to 1 minute, 1 to 2 minutes, 2 to 3 minutes, boom, 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 and they were just all 1 minute in width, then I would still have a histogram that was this shape, the yellow shape, but just all the bars were skinny, right? Because who's going to have a 1 minute commute? Nobody. Very few people. They must live at work. So that corresponding bar would be very short. But I will still experience the majority of the people with a commute up in here. All right, and we can ask questions, easy questions like, what is the probability? Let me give you some notation. What is the probability, P for probability, the probability of the event 0 to 9 minutes commute? And your answer is 0.3. Okay. What about if I changed it to the probability of that the commute was 0 to 19 minutes? It's both of them added together. Right. So it's the height of this bar and it's the height of this bar. Allow me to make one minor modification here just to illustrate my point. I want these classes, I'm going to divide everything by 10. Instead of saying the number of minutes, it will be the exact same scenario except for it would be 9/10 of 10 minutes, and 10/10 of 10 minutes, and 19/10 of 10 minutes. Same amount of time, right? It's the same amount of time. 20/10 of 10 minutes, that's 2 minutes. 29/10 of 10 minutes. You get it? Then I can come over here and say, well, that was a 1, and this was a 2, and that's a 3. So that number on the number line is 1, and this number on the number line is 2, and this number on the number line is 3. And how do we compute class width? Remind me. I've got some classes. How wide are they? I'll tell you. It's not the difference between these two.
What's the difference between those two?
Consecutive lower limits. And so the difference here is 1, right? And that's precisely how wide these bars are. They're 1 unit wide. Now, the bar is 1 unit wide and is 0.3 tall. So then, geometrically, this rectangle has an area of 0.3 times 1, right? The area of that rectangle is just 0.3. So the area of this rectangle is just 0.3. And the next one has a height of 0.5, and the width is 1 still. So it has an area of 0.5. And the last one would have an area of 0.2. And all 3 of those areas add up to 1. Can you remember what the area under the normal curve was? Yeah. So take a moment and see if you can make that connection between the normal curve having an area of 1, it being a smooth representation of an underlying histogram whose bars all have an area, and that area adds up to 1. And then that histogram had a corresponding probability table. And see if you realize that the normal distribution can be used to measure probabilities of events. We use the normal distribution to measure probabilities of events that are normally distributed. This probability table had a normal distribution, and if I was so inclined, I could get a very close approximation to this underlying probability table by just jumping straight to my normal distribution. And if I made the demand that I want 0.8 of the area that is underneath this curve and above the horizontal axis, then that 0.8 area would be the same as this 0.3 plus 0.5, which is the very same as this writing down here, saying that we want to discuss the probability of the event of being between 0 and 19 minutes commute time. And what would happen is I could use some a calculator, a normal calculator, and find out the z-score right there, which is on this horizontal axis, because this is the z-axis, and this is some particular z-score right there. It is this dot, this white dot is that number, z sub 0. It's some number so that to the left of it, the area is 0.8. And if I used my normal calculator to obtain this number, I would expect it to be very close to this. Now, on the standard normal distribution, we had the center of it at 0. Well, this one's not centered at 0, right? And I also don't know what the standard deviation is. So there would be some normal curve. Probably the one that's centered on 1.5 that has some deviation that I'm not sure of. But there is one out there that I could tell it, put 0.8 of the area right here, and the number that would pop out, z sub 0, is 2. So, the message is that we use the smooth distributions to calculate probabilities of events. Let's say, not Maine, mail. The mail is delivered to my box at some random time between 12 p.m. and 1 p.m. Shannon, what's this symbol?
And?
Didn't you ask last time what that was? No? I thought it was you.
I thought that was it. I thought you were trying to make sure I was listening or something.
Oh, no. No. No, somebody had asked me recently, like, what is that crazy looking thing? And I'm like, what do you mean? It's an ant. It's an ampersand. And they were like, they'd like never heard of it. I'm like, it's shift whatever on your keyboard, shift 7.
Oh, that's funny.
Maybe it's a different class. It must have been a different class. Okay, so the mail is delivered to my box at some random time between 12 and 1. Now, this randomness indicates that any of the times between 12 and 1 the mail is equally likely to show up. It's equally likely to show up at 12 as it is to 12:30 or 12:45. This distribution is what you would call uniform because all of the probabilities are equally likely. Then if this is 12 p.m. and down here is 1 p.m., then there is just, so the curve then that would approximate the distribution is a horizontal line. Instead of saying 12 p.m. and 1 p.m., let's say it like this, 0 minutes and 60 minutes. Because that's 1 hour after, that's 60 minutes after 12. Then the height, or the y value that this horizontal line would go through is 1/60. It must go through the y value of 1/60 because tell me what the area of that rectangle would be. 1. It must be 1. And if I'm talking about probabilities, I need to discuss all of the possibilities. And if it can arrive anywhere between 0 and 60 minutes after 12, then having an area of 1 corresponds to me having captured every possible event, right? So the area under that curve and above the, let's call it the x-axis, is 1. Then let's discuss the probability of witnessing the male come in less than 35 minutes. So you would be calculating the area here between it instantly showing up and it showing up within 35 minutes. Then this yellow area is equal to all of these symbols. It is nothing more than the area of this rectangle. And you know how to compute the area of a rectangle, right?
Length times
Length times width. What is the length
35,
and the width?
160.
The area under the curve corresponds directly to the probability of the event. This notation reads probability, event, area. That's important to make sure we get correct, because when you start using that normal calculator, it'll get confusing if you're not comfortable with this notation. It just says the probability of an event is equal to an area. Questions? This okay? Easy? Or not? So what's the probability it arrives in less than 30 minutes?
Yeah. 0.5.
Mm-hmm. It's just half of that bigger rectangle. What's the probability that it arrives between 54 minutes and 60 minutes? What'd you say?
0.9.
So you're telling me that there's a 90% chance that it's going to show up in the last 6 minutes of the interval? Do I have 90% of the area right here in this last 6 minutes?
No.
No.
In the last 6 minutes?
Yeah, between 54
Oh,
and 60 would be just
0.1.
this piece, 0.1. It's a 10% probability that the male would show up between 54 and 60 minutes. It's just 6 over 60. 10%. All right, ready to do some with normal curve? It's noticeably more challenging. Let me first tell you, well, if we did not have this StatCrunch calculator, the gnashing of teeth would begin shortly. But we have the StatCrunch calculator. It makes it painless. Students didn't always have that. I didn't when I was going to school, and we would do it like 1960s style with a, come on, what am I doing? We used a table of numbers. It was horrible. And they still have the links in the homework to these tables, but you do not need to use them or even worry about them. But we need to see what the other people went through. There's a picture here at the top. It shows you a shaded area under that curve. It's shaded in blue. There is some z-score down here corresponding to that area. And then a big table of numbers. And the way this table works is you always do your z-score to 2 decimal places. So let's say my z-score was minus 1. Minus 1.23. There we go. I like 1, 2, 3. So my z-score is minus 1.23. This means I have a normal distribution, and this table, since it told us by the picture at the top that it does this kind of solution, it tells you this kind of area, which is to the left of some negative z-score. And I am saying I want to know the area associated with minus 1.23. This is the z-axis. Then in my table, this is the column for z. I would have to scroll down to the minus 1.2. There's minus 1.2. But this is the column for minus 1.20. And this is the column for minus 1.21 and minus 1.22. And then right there is minus 1.23. It says 0.1093. I have now found that this area in my picture is equal to 0.1093. That's how it would be used. This is the 0.00 column, or excuse me.
0.00.
Yeah, is that what it says at the top?
Yeah.
If it really says that, it's not right. It should be like point, because you don't know that the number right after the decimal is also 0. Because here I'm looking at minus 1.2, right? So I'll label it like this. This is the column for minus 1.20 and minus 1.21, minus 1.22, minus 1.23. And so it is because for the longest time, everyone had to use these tables. That is the reason nowadays, still, everybody rounds a z-score to 2 decimal places, because having any more decimal places isn't going to help you, because your table doesn't do anything past 2 decimal places. So at nearly every turn in the homework, z-scores are rounded to 2 decimal places. There might be one occasion in the whole semester where it's different. Okay, and this number, 0.1093, is an area. It is that area that I have shaded right here. And its symbols, symbolically, that number is the probability that we saw. Some z-score coming out less than or equal to minus 1.23. This thing here in the parentheses is our event. It's the event that we witnessed it come out less than or equal minus 1.23. So it's akin to earlier when I asked about the first question with the 0.2 and the 0.3, and you just added them together, or it was 0.2 and or 0.3 and 0.5. I asked what was the probability our commute time was 0 to 19 minutes, and you ended up just adding the columns together. Well, this is a way of just adding up all of the area associated, or adding up all of the rectangles in the background that we can't see that are our actual histogram. Really and truly, whatever it is you're doing is not going to have a histogram that has bars that have a width of 0, that are infinitely narrow. But this smooth curve takes it all the way to that limit where we let the width of the bars shrink down to nothing, and we can get this smoothness. And then they've done a bunch of calculus in the background to like create this table of all these numbers and find out that the thing has area of 1 to begin with. And we get to use all of those ideas to estimate probabilities of events. That's what this is all about. I'm curious though, before we go on, what would you think is the probability that we saw some z that is bigger than or equal to positive 1.23? Without looking anything up. Shannon, earlier I was asking a question and you said something about cut it down the middle. Cut it down the middle now and answer this question.
We're cutting it down the middle.
Mm-hmm. There, I've cut it down the middle. Where does 1.23 live? 1.23 lives over here. And what kind of area am I asking about? I'm asking about the area that's bigger than this z. 0.1093. It's the same. It's symmetric, right?
Because of the shape of the curve?
The curve is symmetric. So if I just fold it in half, then this minus 1.23 would land right on top of positive 1.23. And the two areas have to be identical. One more question. What is the probability that I saw some random occurrence that was bigger than or equal to minus 1.23? how'd you get that?
1 minus 0.1093.
Because the area under the whole thing is 1. The area under the whole thing is 1, and we're taking away this shaded part, and it leaves us with the unshaded part, which is this number.
And it's 1 because it's symmetric, or is it always symmetric?
It's 1 because it's a probability distribution, right? We had to have the area under the curve be 1. And so then conceivably, any curve at all, any area that is equal to 1 is the probability distribution for something, right? And it's this particular one, the normal distribution, which has an area under it of 1, that is so popular because so very many phenomena out there are normally distributed. We're not going to use that table. We are going to use StatCrunch calculator. If I go down here to get more help in the StatCrunch, it opens the StatCrunch window. Now later on in the future, you're going to be doing an assignment and you're going to be like, how do I get my, so keep it, what I want to say is just keep in mind that you can go to any problem in any homework assignment and open StatCrunch. Boom, there it is. Stat calculators, normal. Brings up my normal curve. When we're looking at this calculator, we are not at all surprised that when half of the area is shaded, that this statement at the bottom is very familiar to us. It says the probability of the event that we witness something coming out less than or equal to 0, well, that would be all the numbers less than 0. The probability of this event is the area 1/2. Literally half of the area. And since this symmetric curve is centered right at 0, then the left half of it gets shaded. This having half of this area shaded corresponds to this number being 1/2. Okay? Oh, I can't say this enough to you. I will say it until you want to scream. Because I'd rather drive you crazy pointing it out over and over again than for you to think that an area would go here. The areas don't go here. The z-scores go here. And it's equal to an area. The probability of an event is equal to an area. And in this problem, what they have asked me to do, they've told me this is a standard normal distribution. So it has a mean 0, standard deviation of 1. And my calculator is so fancy that I can stipulate what the mean and standard deviation would be. And they want to know the area that's to the left of 0.94. Now see that this less than or equal sign is going to mean to the left. Because here is 0.94, and I'm talking about all the numbers less than 0.94. That's the region to the left of it. So when I hit compute, it gives me that area. And here, there's no restriction on number of decimals. I mean, maybe there is, probably, I mean, whatever the computer can handle, probably 8. So this calculator is going to give us a more precise answer than that table would. They always, or typically, they want the area to 4 decimal places. Why? Because that's what that table was delivering, is a 4 decimal approximation. So 0.8264. Okay? Now they want to dress it up for you. They tell you it's still a standard normal distribution, but now it's got a backstory. All right? Now it's got a backstory that the distribution we are looking at is bone density scores, which I guess the average bone density score would have to be 0 because the mean is 0. Right? And 68% of, by the empirical rule, 68% of people would have a bone density score between -1 and 1. Right? That's just the empirical rule that says plus or minus 1 standard deviation gives you 68% of the area. Just a rough estimate. I think it's actually 68.44. And state for me this area here in this language of symbols. What is this area?
It's greater than or equal to -0.96.
That's the event. So I want the probability of that event. So I'll change this to a greater than or equal. I'll put in my event, my z-score of minus 0.096, just negative 0.96. When I hit enter, it draws the same picture. This picture and that picture, they match. I've done it right. .8315. Now, since this one had a backstory of being a bone density score, we need to be able to state what this number means besides just saying it's the area of the shaded region. And what you would say is that 83.15% of randomly selected patients have a bone density score bigger than or equal to minus 0.96. 83% of patients have a bone density score bigger than or equal minus 0.96. So I've reinterpreted this area as a probability of an event. Again, here with the bone density scores. I would like for you to recognize that an area that's like between two numbers this is A and this is B, and I'm talking about my z-axis. You can compute this as the sum of two other areas, or really it's the difference. Because I can compute the first area all the way out to B, the big area all the way out to B, and then take away the part that's up to A. See what I'm saying? It's this bigger area all the way out to B, and then I deduct the part that's just up to A, and what am I left with? Just this slice in the middle. So notationally, this would say the probability that your Z comes out in between A and B is equal to the probability that that Z was less than or equal to B minus the probability that that Z was less than or equal to A. Now in StatCrunch we have a true luxury in that we can compute an area between two numbers without having to do them one at a time. It will help us do it all at once. Up here at the top, there is a button that says Between. And when you click it, look at what changes. The statement down here at the bottom changes to have the A and the B. It has both of them, right? The two numbers. And then over here is still our area. And look, it's even comes right up by default to that first part of the empirical rule, that if you are one standard deviation away from the mean, then it's about 68% of the area. And here in this problem, they are talking about the probability that a patient has a bone density score between minus 0.82 and 1.22. And the probability of that event is 0.6827. So, once again, the probability that one of my patients has a bone density score between these two numbers is 68%. 68% of my patients fall in this range. Probably every phenomena having to do with, well, let me be careful. I can think of at least one, like, healthcare related phenomena that's not normally distributed. And it's not even really healthcare. You know, the prevalence of diabetes among people normally distributed, the prevalence of heart disease, your pulse rate, people's blood pressure, the likelihood that you'll survive some such and such surgery. Everything is normally distributed. And the only thing I can think of that's not is age. Because there's a whole lot more, it's skewed to the right, right? Age is skewed to the right. It's looking like this. Like we live a long time, but maybe it used to be normally distributed back whenever, you know, a saber-toothed tiger would eat you and you'd die at 30. But now we live a lot longer, and so it's skewed to the right. Okay. I'm going to switch my calculator back to standard. Let's study this picture that they've given us. Let's read the instructions. Read the instructions, study the picture, and then tell me what is this number indicating. It's the area. It's the area. I've had so many students, though, look at that picture, and where do they end up putting this number? For the Z. They don't go there. It's an area. They're saying there is some Z-score that would yield this area to its left, and they want you to produce that Z-score. And if you thought the last trick with StatCrunch calculator was luxurious, this one is the whole. I mean, if it didn't do anything but help me with this problem, it would be worth it. If you had to do it by the table, imagine what you would have to do. You would have to come in here into this table. You would have to find that area, whatever it was. Was it 0.9082? It was. So it was actually not too hard. I scrolled right to it on accident. There's 0.9082. And look at the Z-score it corresponds to. 1.33 corresponds to 1.33. When I go to my StatCrunch calculator, I can just type in the area, 0.9082, and look how the Z-score goes blank. Because when I hit enter, it will deliver back to me that Z-score. Except for I didn't do my inequality correctly, so I'm looking at the symmetric version of it. They wanted. Then now the picture that I have on my calculator matches the picture that they gave me. I've got a curve, it's got an area of 0.9082, and I can see what that Z-score is that makes it happen. It's 1.33. So you can visualize when I started teaching here, big room full of students, and everybody's got that stupid table. We didn't have this. We did it by hand. on paper. Took paper tests and everything, and I'm having to help everyone, find the number in the chart and backtrack, and it's just like, so this calculator is really where it's at. It's a big help. Question 5. They give us the shaded area. They want the z-score. That does it. So, which way does my inequality need to point?
The other way.
Yeah,
Greater than.
to be greater than. Because it's the area that's greater than some unknown z-score. And that area is 0.1251. I get a z-score of 1.15. And if you didn't have to listen to me yammer on about all this nonsense, you could do this homework in about 5 or 6, 7 minutes. Like, it really wouldn't take any longer than that. And when you get to the, so then by the time you get to the quiz and the next midterm, hopefully you can leverage that time saving and the correctness of the calculator. All right, well, now they've really got a backstory going. It's about IQ scores. There, I left that one out. That's something having to do with people that's normally distributed, IQ scores. Let's do this one, and then we'll go on our break. Now, we're going to do this 2 ways. At first, we're going to pay our dues and pretend that we cannot change the 0 and the 1. And then once we've seen it the one time, we'll use this. Because here, look, that's an IQ score of 80. This picture exactly says, what percentage of people have an IQ score less than 80? That's what it says. Can you see that in that picture? Yeah or no?
Yes.
Tell me the truth. Do you get it?
Yeah.
Okay. Because the mean is 100. So 100 is right in the middle. And the standard deviation is 15. So it's like this distance right in here is 15. 80 is 20 away from 100, so that's why it's to the left of the standard deviation. And what we would have to do is get z-scores. I would have to get the z-scores. I would have to get the z-score for this 80. Right? Do we remember how to do that? Z is the observed minus the mean over the standard deviation. It just standardizes whatever you're looking at back down to the standard normal curve.
80 minus 100.
Over 15. So it's negative 4/3. Okay? Then I would have to be going to my table. I'd be looking up minus 1.33 and finding the area to the left of it. And I'd be getting 0.2 .0918 for that area. And then I'd be able to answer the question.
Really quickly.
Yeah.
So what I basically did was I plugged in, I kind of did it, I just plugged in everything. Like I put-
But at first, we are pretending that we can't change these
Oh, okay,
and examining what happens.
right.
And then we're going to come back and enjoy this luxury.
Okay.
And the reason being is that I wanted the opportunity to remind us of this Z-score calculation because it's going to come up next week, and the following week, and every week. And only because of this, having this calculator, do we even get to like sail on past this. If you know, back in the day, we did every problem this way. Now, so I get the answer 0.0918. Let's now compare and I did that using this Z-score, minus 1.33. Okay. But minus 1.33 is not equal to this calculation. It's just an approximation to it. The thing it's really equal to is minus 4/3, which is a different number than minus 1.33. So the answer for the area that we're going to get down here is going to be a little bit different, but probably not different in just four decimal places. So our mean for these IQ scores is not 80, it's 100, and the standard deviation is 15. And we're talking about an IQ score less than 80. And they get 0.0912. So it was different in the fourth digit. And that's why I was saying earlier that using the calculator is more accurate than the old methods with the table and everything. Like 0.0912 is the correct answer. 0.0918 is an approximation, and the error is happening right here.
But because it would be 9% either way.
If you ended up rounding your area to 2 decimals, yeah, then you're just saying 9%. But if for whatever reason that fourth decimal place is important to you, then it's different unless you have this more accurate technique. Okay. And it's just saying that 9%, that seems like a lot. 9%. This is real numbers. Like this is supposed to be the fact of the matter for people. And that nearly 10% of people have an IQ under 80. It's kind of alarming. Especially when in the past 100 years, IQ scores have gone way up. All right, break time.
guys feel about the midterm?
It was okay. One of them I was really mad because I did a typo on it.
Mm.
You know, like my way back, and I was like, son of a gun. you know? And then there was two questions on the same concept that I did not get.
Yeah,
Yeah.
with the, was it the one where for some reason, opened it in StatCrunch, I typed it into StatCrunch, I got the standard deviation and the mean,
Yeah.
and that it wasn't
Yeah, it was, I think it was one of the, no, actually, I had a hard time, I still kind of have to really talk myself through it, but we covered last week.
the K equals, that, or L equals K over 100 to the, that was.
Yeah. But my microbiology test, that one really kicked my butt. But a
Was
lot
it
of
the
people in
same?
the class say that it could kick their butt too, so
Yeah,
that-
micro.
it makes you feel a little better. Like, it makes you feel less dumb
Yeah,
when everybody's struggling with it. Yeah.
micro was a trip.
I feel like I felt really good going into it, but then the questions, I felt like the testing questions did not align with like what we had done going up to it.
Oh, really?
Yeah.
Here.
Yeah.
Was it similar to was it online also? Okay.
I just started in math class, not gonna lie, like last class.
Oh,
Yeah. And it was so behind, so I haven't even started the midterm yet, because I'm trying to catch up.
from that,
Yeah.
okay.
I have 2 other classes as well that I'm taking.
So you're taking 3 right now?
Yeah.
Is that a lot?
It's a lot. I also work and have 2 kids at home.
Yeah, that's
So
a lot.
I'm like, how am I supposed to balance it all?
Yeah.
Wow.
So
That is a lot.
I'm trying to figure it out, and I'm terrible at math. So it's not something I'm ready to jump into.
Right.
But I'm trying to get there.
You'll get it. Did you have videos to help myself understand the thing, that we were the L over K, they have videos on the, like my math lab. I just watch that because sometimes it's
He's
like,
confusing.
I know.
I had him for a
But-
math class last semester for something, and he did the same thing. I was like, I don't know what you're talking about here.
They have videos on that. Sometimes I get it and sometimes I don't. So I'm like, okay. What other classes are you in?
I'm in speech and philosophy.
Yeah, okay.
They kind of go hand in hand, but at the same time, they also require more than if they want us to record ourselves talking speech. And I'm not the best speaker, so I have to go through it like a thousand times. And I'm like, okay, and now I'll hop on for now. But that time it's at midnight, and I'm like, okay, for a little bit. But I'm hoping to begin my actual nursing core classes by June.
Oh, that's awesome. Oh, August.
June. Really? You're gonna get there that quickly? I'm gonna be in mine in June as well. Yeah, so we might be
Yeah.
together. What was your name? Alexis.
I'm in this in foundation higher education. Yeah, super good. Now I have Dr.
Walter?
Yeah, he's fun.
Mhm.
Does he still do the vodka? I'm
I'm
joking.
Yeah,
What did he say? I'm
It says
kidding.
it was moonshine.
Oh, okay. Yeah, but he chooses a different adult beverage each time. And then,
Anything clear.
Yeah.
It says Jones water. Maybe laugh out loud though.
What is the probability in, what is the statement that interprets this picture in terms of probabilities of IQs. This area is equal to,
The probability,
The IQ is greater than 70 but less than 115.
yeah, or between 70 and 115. So then I can change my calculator to between. I can tell it those two IQ scores. Evidently, it's nearly an 82% likelihood that that would occur. So you can go out and pick a randomly selected person from the population, and 82% of the time, their IQ score is between 70 and 150. Alternately put, the entire population, 82% of them have IQ between 70 and 115. It's essentially the same statement. What do I do?
Area.
The area, 0.97. Do I have the right inequality?
yes.
97% of people have an IQ less than 182.2. Or I said 182, I meant 128. 128.2. Now the area is 0.6. The inequality needs to be to the right of some number. See that the picture you got matches up. Like more than half of it is shaded red, right? And 0.6 is more than a half, so we're on the correct side. And what is the probability statement for this? What does it mean in words?
What is the probability that people have an IQ greater than?
Well, we know that probability now, don't we? So you can complete
So
the
60% of people have an IQ greater than 96.1997.
Yeah. Or you could say one randomly selected person will have an IQ score more than 96.19 60% of the time. And then now they remove our crutches. There's no picture anymore.
This is a between problem. Is that mine it is?
Yes. It will be a between problem at first. Well, in both, it's a between problem. Correct. So we have women's height's normally distributed. They've told us what the mean and standard deviation is. So it's a they say it's normally distributed, so here's my normal curve. The mean is 63.9 and the standard deviation 2.4. So that means that this distance is 2.4. And it says that some branch of the military requires women's heights to be between 58 and 80. I don't know why there'd be it's like you're too tall to be in the military.
It's a true thing.
Really?
It's real.
It's like,
Too tall to be in the military.
it depends on like your job. Like helicopter pilots have to be below a height to be
Yeah.
able to move the controls the
You
right
don't
way.
fit in the
Yeah.
cockpit.
Yeah, and then too short because you can't reach everything to manage it. Same thing applies for like being able to be fit in a tank, do the stuff that you have to do.
Ain't like other stuff they could do, like cook. Now I'm going to go out on a limb here, and before I've even made the actual picture with StatCrunch, I think it stands to reason that an overwhelming majority of women are between 58 and 80 inches tall. All right? This is like 4'10"
Yeah.
and 6'8". And that's probably almost everyone. Right? I mean, I'm totally confident it's more than 90%. It's probably up around 98 or 99%. So this area that I'm going to get here is going to be the majority of the area under this curve. And what are they asking in Part A? Is find the percentage of women meeting the height requirement. So the area that I get, I'm going to convert it to a percentage, just like we've already been talking about. And that's going to be my answer. They ask a follow-up question. Are many women being denied the opportunity because they are too short or too tall? And since we've already decided that this is going to be a huge chunk of the area, then it's probably going to be the case that not many. It would just be this area in these tails, whatever percentage that is in these tails. That's the percentage of women being denied entry. So the mean is 63.9. Standard deviation is 2.4. And I guess I want it to be between 58 and 80. .3%. 0.30% rounded to 2 decimal places. Are many women being denied the opportunity to join? No, because only a small percentage are not allowed to join because of their height. Part B. This branch of the military changes the height requirements so that everyone is accepted except for the bottom 1% and the top 2%. Then what are the new height requirements? What do we do? If I wanted to figure out which height is associated with the lowest 1%, what can I do? It's normally distributed, right? And the heights are on the horizontal axis. Ideas. I don't care if it's a wrong idea. I love wrong ideas. If you're telling me the right thing every time, then you don't need me. It's normally distributed. What percentage, let me ask you like this. What percentage are shorter than 63.9? 50%.
Now 51%? I know.
It's 50%. Because this is half of the curve. This is half of the area right here. That's 50% of the area. And that 50% of the area is coming out shorter than this height. And what we are wondering is which height.
So do we do 49%?
So 49% would be,
Because then we get the bottom 1%.
would that be 1% of the area right there? When you're thinking, so where does your 1% live? That 1% that you're talking about is the people.
I want it on the other side. Like a little.
Mm-mm. So that 1% that you're thinking of, where you said 49%, that would give us a height of 63.83. So 63.83 is awful close to 63.9. And only 1% of women have a height between 63.83 and 63.9. So that's not where I want the 1% to show up. Where do we want the 1% to show up?
You want,
Little
and
tail on
you want to
In the
put
tail.
the probability, we need to take out the 63 and put equals 0.10, 0.1. And so probability.
Point 1,
0.0.
0.01.
Yeah, 0, 1. And it's less than, yeah.
Now we have a picture of the bottom 1%. So this red shaded area that extends into the tail out to infinity is 1% of the area. And the corresponding height, go away, corresponding height right there below the edge of that red is 58.32. All right, and, okay, so that's the lower limit, 58.3 inches tall. You have to be taller than that.
Flip it,
Flip the inequality.
and 2 points, 0, 2.
And you have to be shorter than 68.8. Which is a shame, because that's like a normal height, isn't it? Surely.
Yeah,
Yeah.
I'm 68 inches.
Yeah, I was about to say.
That's 5 days.
Yeah, that's a normal height. But that, I mean, that's what 2%, that's what the top 2% comes out to be, so 68.8. They must have some tiny airplanes. Little miniature tanks. Excellent. All right. Question 11. The lengths of pregnancies are normally distributed. Big surprise, right? Some of them are short, some of them are long. The majority are normal. The majority of them happen right around the average time. It says that the typical pregnancy is 267 days. The standard deviation is 15. Oh boy, this question. In a letter to an advice column, a wife claimed to have given birth 309 days after a brief visit from her husband, who was out of the country. What is the probability that a pregnancy could last 309 days or longer? You see what this is getting at? So, what am I going to type? Find the probability that the pregnancy lasts 309 days or longer than that.
Probability that pregnancy lasts, so is greater than 309.
Okay. Then what does this mean in the context of this question? What's going on here? She gets a brief visit and gives birth 309 days later. And this is the probability that you could have a pregnancy last that long or longer. Not many of them, right?
I just, beyond the probability is low. I also made a comment. If he came at that time, she had the pregnancy for that long, I don't think that's his baby. But that's just-
It doesn't look like it. It doesn't look like it. That's the follow-up question that they ask.
Oh, really?
Yeah. That's the follow-up question. They said, what do the results suggest? It kind of suggests here that, I mean, it could be. It very well could be. But it only happens about 0.25% of the time. So the probability, they don't want the percentage here, they want the probability. So just the number, 0.0026. And then there's our answer. It could happen. It could still happen.
A rare event occurred.
Yeah. It could happen, or it's not his baby. Part B. Some institution out there had decided that if your pregnancy is in the lowest 3% of lengths of pregnancies, then the baby is, by definition, going to be premature. This 3%, I'm sure the authors of this question just picked it. I don't know what the real number is. But here we're going to pretend that a baby is by definition premature if the pregnancy is in the lowest 3% in terms of the gestation period of all pregnancies. All right. We should be experts by now. How do I do this?
Less than, equals 0.003. Or no, 10, 0.03, sorry.
So then that red area is 3% of the area. And bang, 239 days. 239 days or less, then that would be a premature baby. Question 12. I love this question. It's about body temperature. You see, I'm certain that in your textbooks that are, medically related, there's something in there that says it tells you what average body temperature is. But how did they get that number? I mean, did they just ask a bunch of random, doctors and nurses what it should be? Did they just say, well, we know it from our experience? It's about this. Absolutely not. They would have gathered a bunch of people as a sample. That sample would be demographically similar to the population of all people. They would have taken everyone's temperature at a bunch of different times. They would have found the mean temperature. They would have calculated a standard deviation from that sample. And then the hospital, down at the hospital, they don't want every Joe Schmo with a runny nose to be coming through saying, that they need to get admitted. We only want, we want to have a firm cutoff for, we want a clear definition of what it means to run a fever. Not just because, mommy said my forehead was hot. And at this hospital, the number is 100.6. Then we wonder essentially, is that a good, smart choice? Given that this is the behavior of our population, is 100.6 a smart choice for this hospital to use as their definition of a fever? It's like, if your temperature is 100.5, not a fever. If it's 100.6, now it's a fever. And all the temperatures, 101, that's a fever too. So what do? I want to calculate, what does it say? The percentage of normal and healthy persons considered to have a fever. Because after all, these numbers, 98.19 and 0.063, these aren't sick people. Sick people are a different population. This is normal and healthy people. This is the behavior of normal and healthy people. And the goal with this cutoff is to say, we don't want normal and healthy people like slipping through into the, getting a room because, and then come to find out they're really not sick. They're normal and healthy. So then I would wonder, as like a hospital administrator, how often would it happen that somebody would have a fever per our cutoff? It shows that they have a fever, but yet when we check, they're fine. They're normal and healthy. How often does it happen? That's the question. What percentage of normal and healthy persons would be considered to have a fever? I'll get us started. I know that we need to put the mean and standard deviation. I need you to tell me the rest.
What percentage of normal and healthy people would have a temperature greater than 100.6?
That's the question.
So I put in greater than 100.
Put it greater than.
Period. See, 100.6.
You want to put 100.6 here?
No,
No. The area won't go bigger than 1.
put 100.6 there.
Yeah, that's the event. Right? The event that this person, X, had a temperature, this normal and healthy person, X, that there is nothing wrong with them. They feel fine. But I put the thermometer in their mouth, and it comes out 100.6. Or it comes out a number bigger than 100.6. It's essentially no one. It can still happen. This says 0.00006, blah, blah, blah. Rounded to 4 decimal places. Rounded to 4 decimal places, that's 0.0001. Right? which is this fraction. So, what it's telling me is that for every 10,000 patients that come through with a fever, one of them's not actually sick, and the other 9,999 are. And they want me to type in a percentage. What should I type in?
0.0001.
So this is our number. 0.0001 is a number. We need to convert that to a percentage.
But even if you convert 0.00006 to a percentage, it's gonna be 0.006%. And it says 2 decimal places, and that's 3. Does that make sense?
Mm-hmm.
Okay. But I feel like putting 0% in there also isn't.
So if this had said, if this wasn't a 6 and was instead a 4, you would type in 0 and hit enter and it would be right.
Okay.
But it's not a 4, it's a 6. So to 4 decimal places, I would have this.
Oh, 0.001.
Too many zeros.
1 0. 0.01. Okay.
0.01%.
Is
So-
it rounding up after you?
do the 4 decimals, and then, I mean, either way, you'll get it done, right? If I convert this number to a percentage, then it's just 0.0065 whatever, and then round that to 2, it'd be 0.01%. Keep in mind that the percent symbols, all they mean is, divide by 100. They mean divide by 100. You can, they're interchangeable. They're interchangeable. So you can verify that 0.01% being equal to 0.01 divided by 100 really does come out to say 0.0001. You can be completely confident that you've converted it correctly. So it's 0.1%. Hardly anyone. Well then, is the cutoff appropriate? Is a bunch of riffraff getting through? Are we catering to a bunch of hypochondriacs? No, we are not. There is a small probability that a normal and healthy person is going to have 100.6 on the thermometer.
I think it's yes,
I know,
because of the
Oh.
way the question is.
Sorry, I
Is
clicked
it-
the wrong
is it-
one.
Is it appropriate? And it's yes, only a small percentage.
Yeah, I
Yeah.
wasn't paying attention. You're right. Now, there's a different criteria, a restrictive criteria. We don't want to be overloading the lab with a bunch of unnecessary tests. So we're going to say that you need to, they're going to establish a minimum such temperature for you to get a test. And it's like, if your temperature is coming out below this, you can buzz off. Not really, but you can go see your PCP, complain to them. The minimum temperature for requiring further medical tests. And we only want 5% of healthy people to have a temperature that could ever be higher than that.
The area is 0.05.
Then the picture literally says to us that 5% of normal and healthy people have a temperature that's more than 99.23. We good? That's the assignment. Now, the StatCrunch calculator makes this assignment reasonable. I want to go ahead and do the first couple problems from the next homework because they are right along these lines and all this is fresh in our mind. Because on the next assignment, it's a couple of problems like this, and then something that's completely different and way harder. So I'll go to homework 5. And then secretly tell you something that you've been doing the whole time you didn't realize. So when I would go through and say all those probability statements, often I was saying that one randomly selected person that met this criteria had, it had this percentage chance of occurring. Each of those questions that we just did was about one person, a single person being selected at random. But you can do this stuff for any sample size you want. You can have a sample size of 10 or 2 or whatever. And you can do it, and everything works just the same with one exception. You end up dividing your standard deviation by the square root of your sample size. So recall that little n is our sample size. Right? And we used sigma for the population standard deviation. Then I want to define a new distribution. And your distribution is just that smooth curve. I want to define a new distribution, which is called the distribution of the sample mean. And the symbols that we used for the sample mean was X bar. So I want to talk about, well, let me say one more thing. We also would have had some mean. So my population has some mean, it has some standard deviation, and I go out and get a sample of size n. I go out and get a sample of size n, then that sample has a sample mean. That sample has a sample mean, and what you can do is you can construct a new distribution from the old population. I go out and I get a sample, let's say it's size 5. I go out and get 5 people, I find their mean, and I start making a list. And the first time I did it, I got a mean of 10, and the second time I did it, it was 12, and the third time I did it, it was 8, and so on. And I do this thousands and thousands of times. And the millionth time I did it here, I got 11. And there's a bunch, I got all these results here in the middle. So this is a big list of data. It's a big list of sample means. Each of these is a sample mean. If you set up some classes and made a histogram, this would be normal. Every time. No matter what was going on over here. This could have been skewed in the craziest way. The distribution of the sample means will be normal without fail. So, it will be normal without fail. And it will have the properties that the mean of the sample means. This little subscript is talking about that distribution, the distribution of the sample means. The average of these numbers in this list will come out to be exactly the same as the mean of my original population. They're identical. And also, the standard distribution of this data turns out to be equal to the old standard distribution divided by the square root of n. So what this is saying down here is that the distribution, this other brand new distribution that we're talking about, that has to do with multiple people in a sample instead of just a sample of size 1. I now know what its mean is and what its standard deviation is. The standard deviation of that new distribution is simply the standard distribution of the old population divided by the square root of my sample size. And they have the very same mean. Statisticians go nuts over this. This is probably their favorite thing in the world. Not mine, but they go all gaga over. Oh, it's so fascinating because it's true anywhere in the universe. So are a lot of things, but. Now here I am on question 1, homework 5, and they've got a question here that's just like what we were just doing. I I have a mean of 74, a mean pulse rate of 74 with a standard deviation of 12.5. So females have a pulse rate that's normally distributed. The average is 74, standard deviation is 12.5. Awesome. Well then, because it's normally distributed, I can use this normal curve to calculate probabilities. Then the probability that a randomly selected adult female, that means the same thing as one randomly selected adult female. So then my sample size here is 1, right? And the square root of 1 is 1. So if we're talking about a sample of size 1, then it collapses all the way down to the original type of problem we were doing. But if my sample size grows more than 1, then I just divide the standard deviation by the square root of n, and then you have the new standard deviation. So they want to know, find the probability her pulse rate is less than 81 beats per minute. The probability is 0.7123. Part B, well, now it's a group of adult females. Now they have 25 adult females being randomly selected, and they want the probability that their average pulse rate is less than 81. Do you think that the probability will go up or go down or stay the same? What you thinking on that? So isn't 81 above the average? The average is 74, right? And 81 is more than the average. So, so then for a single female, it says that there's a really good chance that their pulse rate is going to be less than that number, which was already a little bit high. But now we're getting together 25 people, finding their average pulse. Wouldn't it be a more difficult thing to do to find, so tell me what's more difficult, having one randomly selected person with a super high pulse or having 25 people that you randomly picked and their average pulse is high? Which one's harder to have happen?
So I think randomly selecting 25 people that have the average of a higher heart rate.
Yeah. It's like saying, somebody has some rare medical condition in the population. And yeah, it's a low probability that when I randomly select someone, they have that rare medical condition. But it's way more rare for me to go and get randomly pick 25 people and they all have the rare medical condition. That's a harder thing to have happen. So then, the probability that my collection of adult females here is going to have a pulse that's less than this bigger number, that's a strong likelihood that that's going to happen. Because on the average, people have the average pulse rate. And the bigger that my sample size will grow, the more difficult it will be to have a group of people that exceed that pulse rate. So, what I'm needing to do is I'm needing to divide that standard deviation by the square root of 25. Now watch what I can do right here in the StatCrunch calculator.
I don't need to get out my other handheld calculator and computer number. I can just press divide by 5, because 5 is the square root of 25. And it says that nearly every time you go and get a group of 25 females, their average pulse is going to be less than 81.
Why did you divide by 5 again?
Because some smart statisticians were able to calculate that the distribution of the sample mean, this other distribution, has a standard deviation, which is the old standard deviation divided by the square root of the sample size. And the sample size is 25. Square root of 25 is 5. So I just divided by 5.
My number was 4 instead of 25, so I did 12.5 divided by 2.
Yeah.
Okay. Just because my graph doesn't look as shaded in, but it's probably because it's 4
Yeah.
instead of 25.
Mhm. Yeah, I mean the bigger my sample size goes, the easier. So the bigger my sample size goes, the taller and skinnier my normal curve will get. If this is a, let's see. If this is a normal curve, and I have here let's just say the mean is 0, and then that would make the standard deviation right there be 1. It's got an area of 1 underneath it, but if that standard deviation starts to shrink, I mean that's what's going to happen if I start dividing by a number bigger than 1, right? Divide it by something that's bigger than 1, then it's going to be a smaller number. So then, let's say I divided it by 5. So the standard deviation would only be 1/5 as much, which tells me that the inflection point would need to be at 0.2, right? So it'd be looking like that's not even good enough. Maybe I'm making it too tall. There we go, sorry. It turns into, it's literally called a hat function. As the standard deviation starts to collapse down, it looks more and more like a hat. And they call it a hat function. And so it eventually just becomes a step. It's just nothing and then everything and then nothing again. And so they're both normal curves. But for, so like, if I was talking about the probability of being less than 1 on the old curve, it would have been a bunch of the area. But now if I say the probability of less than 1 on the new curve, it's everything. You only have this tiny sliver in the tail, whereas on the old curve, you had a much bigger tail. So as that probability, or as that standard deviation shrinks down, as the standard deviation shrinks down, more and more of the data points are near the center. Which is why our probability went up. All right, part C. Why can the normal distribution be used even though the sample size does not exceed 30? So only thing I didn't say earlier was that this fact here, that the distribution of the sample mean is normal, whenever whenever one of the following two things occurs. The original distribution is normal, or you have a big sample. And so that's just telling us that you can start with something that's so far from normally distributed that it's unbelievable. A good example is like that I've seen is depths of earthquakes. They don't happen. They are not normally distributed. They're far from it. However, the average depth of a bunch of earthquakes will be normally distributed. And we are authorized here to use the normal distribution because our original distribution was normal. I always thought this question was worded in a very silly way. And I still go back and forth about what they mean. I'm pretty sure that what they mean here is that adult females stick their arm up over their head, and then how tall can they reach? Normally distributed, just like heights are, no shock. And the mean is 195 with a standard deviation of 8.3. Part A, find the probability that one randomly selected adult female has a reach distance that's bigger than 207.5. So I get this number, 0.0660. Find the probability that the average overhead reach distance of 20 females is bigger than this 193 something. So my standard deviation is going to shrink down. You're going to have more and more of the observations occur near the mean. It has the very same mean. Now you can go to your calculator and type square root of 20, but you can also say divide by square root, open parentheses, 20. Of course, I didn't put the right number here. It should be 193.5. But I can just type this in to my standard deviation and it'll compute it for me. And then I don't have to transpose anything, I don't have to round anything. So 8.3 divided by SQRT. SQRT is for square root of 20. Because in all likelihood on this problem, you are also given a number that doesn't have that's not a perfect square. All right, 0.7905. And why can I do this? Well, it's because the original distribution was normal. Last one for the day is number 3. The freshman 10, or whatever it's called, 15 or something. So assume that the amounts of weight gained during your freshman year is normally distributed, as most things are, and that on the average, these male students are gaining 1.3 kilograms with a whopping standard deviation of 4.7 kilograms. So that means some people are losing weight, right? Okay. And some people are gaining quite a bit more. All right. My sample size is 1. So so it devolves all the way down into that previous thinking. And if we pick one of them at random, what's the probability that they gain between 0 and 3 kilograms? 0, 3, 25% chance. Now, instead of just picking one, I'm picking 16 of them. And it would be harder. It would be more rare if I'm doing truly a random selection. And since some are losing weight and some are gaining weight, it would be rare for me to go out and pick 16 of them and they all gained weight. Yeah. So then the likelihood that the average of these 16 is between 0 and 3,
It's less than 25%.
so the standard deviation is going to get smaller, right? It's going to be, we're going to divide it by 4. And everything else will be the same. So 4.7 over 4 is a little bit bigger than 1, right? So we're going to end up with a normal curve that's looking like this. Actually, let me back up. Since the standard deviation is going to be about a little bit more than 1, then that's about where 1 is at, right? And right there is negative 1. I goofed up. My middle is here at 1.3. And it would be over here at 2.3. Well, it'd actually be at like 2.5, which is where my first standard deviation is, and then 1.3 minus a little bit more than 1 is about 0. So we'll say that the other standard deviation will happen pretty about above this line. We'll have many more of the observations occur close to the mean, but we will still be talking about between 0 and 3 kilograms. Do an analysis on the tails. Look at how much white space is in the tails on this old one. And the new one, the white space, it must have gotten smaller because this curve is actually way, way, way taller than what I have indicated here. It is far and away taller than the old one. And it must behave that way in order to maintain the property that the area underneath it is 1. So in their calculator, what they do is they just always change the scale at the bottom. The picture stays the same. But if you kept the scale the same and changed the picture, it would get taller. See how it's 0.35 right there? But what it was 0.08. So it's nearly 4 times as tall. Nearly 4 times as tall, and the standard deviation is happening, just right about nearly right at the edges of this interval. And so you have tails that have much, much smaller area, and that forces the rest of it to be in the middle. And if I changed this, if it was 25 people, it's an even bigger area. And if it was 36 people, it's even more than that. And if I did 100 students, it's more still. And look how tall that curve is. And if it was, 1,600 students, then it's guaranteed that their average is between 0 and 3. That's actually a misstatement. The calculator has just given up and can't compute 0.999. It can't put enough 9s here, so it just says it's 1. But there's still an extremely slim chance that if I got 1,600 of the college students randomly selected, that their average could be outside of that interval, given that the college students behaved with these 2 parameters. So as the sample size goes up, the probability will go up. If the limits of the event stay the same. And the question, the part 3 of all 3 of them was that you can do it because it's normally distributed.